Hey, 20-2s. In this lesson, we're going to look at deductive reasoning. So remember the last few lessons, we've been looking at inductive reasoning. And inductive is simply when we're looking for an example, or we're looking at an example, and we're trying to make a conjecture. And we didn't know if our conjecture was really true or false. It was just a good educated guess. Okay, what we're going to do in this lesson is the most important part of this lesson, in my humble opinion. It's talking about showing me that our conjecture is always universally true. Okay, so deductive reasoning will be taking a general observation from a set of data, so our conjecture, and making them universally true, meaning it's always correct. You could bet your house on it. Okay, so here's a common one that we see. You've probably done one of these when you were a kid, right? So someone says, choose a number. Okay, I'm going to choose 10. It's easy to work with. It says double it. So I get 20. Add 5, 25. Add your original number. Okay, 35. Add 7, 42. Divide by 3. Divide by 3. What do we got? 14. And then subtract your original number. I get 4. I'm even run out of room. Okay, so I started with 10. I got 4. All right, well, I don't know. I don't see a pattern there yet, so I'm going to try it again. So I always like to do these things a couple times and make a pattern. So choose a number. Okay, I'm going to choose 5. Double it, 10. Add 5, 15. Add your original number, 20. Add 7, 27. Divide by 3, 9. Subtract your original number, 4. Okay, look at this. I've done this twice. Both times I ended up with 4. So if I was to make a conjecture, what I'm going to say is I'm going to end up, no matter what number I choose, I'm going to end up with 4 as my answer. This is, again, inductive. I've got an example, and I'm just seeing what pattern comes out. I make a conjecture. That's inductive reasoning. Deductive, friends, is this. Choose a number. I choose X. That is any number, right? That's what X means. I'm going to double it. 2X. I'm going to add 5. 2X plus 5. I add my original number. So 2X plus X is 3X plus 5. Add 7. 3X plus 12. Divide by 3. That is X plus 4. And then it says subtract your original number. Well, X plus 4 minus X is, guess what? Just 4. So what I just did here was I just proved my conjecture using deduction. So the difference between induction and deduction is that induction, I'm looking at a pattern with some random examples. Deduction, I'm using, a lot of times I'm using X, I'm using a variable. So I'm showing it's true for all examples. That's universal. Okay, so that's the big difference for today. Now, I need you to know some definitions as you're going through these things. So the next one says, prove the sum of two odd numbers is even. Okay, so let's do induction first. So the sum of two odd numbers, 3 plus 5 is 8. Yep, looks like it's right. All right, I look for a counter example. Minus 1 plus 7 is 6. Okay, so it looks like whoever did this conjecture looks right to me. Let's prove it. Let's show it's true. So an odd number, friends, here's the definition I need you to know. We're going to start with even. An even number is divisible by 2. What that means is 2 is a factor of it. So an even number we call 2n or 2k or 2x. I don't care what you call it, but it's 2 times your given variable. An odd number then is an even number plus 1. So think of any even number, 6. Add 1, 7. You get an odd number. Or I could go 6 minus 1. So I need you to know that an even number is 2 times n, or sometimes you see k. I don't really care. Call it any variable you want, but it's 2 times it. And an odd number is 2n plus 1 or 2n minus 1. So if I want to prove this conjecture, I'm going to add these together. So I'm going to say 2 odd numbers. Well, here's an odd number, and here's an odd number. Right? Okay, I'm going to add them together. What do I get? 4n plus 2. Well, how do I prove that something's even? Something is even if it has a factor of 2. So I'm going to factor out a 2. And what that tells me right there is that this is divisible by 2, which then tells me, therefore, this is even. Proved. Just like that. Okay? So a definition: even, 2n, odd, 2n plus 1 or 2n minus 1. Okay, let's try a couple more of these. They take a little bit to wrap your head around what you're doing. Okay? So how do I show a number is odd then? I just showed that it was even. To show a number is odd, well, an even number is divisible by 2. An odd number is not divisible by 2. So if I have just any odd number I can think of, 2n plus 1, I can't factor a 2 out of this. And if I can't factor a 2, it is odd. Simple as that. If I want to show something's divisible by 4, well, if something's divisible by 4, what I'm trying to show then is that whatever I had, I can factor a 4 out of it. Okay, that 4 there would tell me I'm divisible by 4. If I want to show something's divisible by 5, I have to be able to factor out a 5, right? And so on and so forth, right? Divisible by 99, I got to be able to factor out a 99. Okay, so that's going to come up as you're doing your work. All right. Try another couple here. Write a conclusion which can be deduced from each pair of true statements, right? These are true, I guess. So Leona lives in 100 Mile House. 100 Mile House is in BC. Okay, so what can I deduce from that? Well, if she lives in 100 Mile House and 100 Mile House is in BC, well, then I can prove to the judge then that Leona lives in BC. Okay, so again, it's not always deduction isn't always just using variables like I was doing in the first example. Sometimes it's just using a couple of really true statements and linking them together. All right, let's try another one. Steve is taller than Nick. Nick is taller than Gordy. So what do I know? If Steve's taller than Nick and Nick is taller than Gordy, then what I know? Steve is taller than Gordy. Okay, so an easy example of deductive reasoning. Okay, not too bad, not too bad. Okay, here we go again. I want to do this number choice one just one more time. Okay, it seems to pop up quite a bit. So these little number trick ones. So when you get one of these, like I've typed this table up for you, but when I get one of these things, what I like to do is I do inductive a couple times, and then I do my general case for deduction. So what I want you to do right now, friends, is hit pause on the video, pick a couple of numbers, and see if you can create a conjecture. See you in a minute. Okay, let's see what you came up with for a conjecture. So it says choose a number less than 10. 5. Add 4, 9. And keep in mind what number you started with could have been different. Doesn't matter, right? Double it, 18. Add 7, 25. Add the original number, 30. Divide by 3, 10. Subtract the original number, 5. Oh, I ended up with what I started with. Okay, try it again. Choose a number less than 10. 2. Add 4, 6. Double it, 12. Add 7, 19. Add on the original number, 21. Divide by 3, 7. Subtract the original number, 5. Oh, so now you can see by doing this twice that my original conjecture was incorrect. I was going to say I end up with my original number, but now what I actually think is going to happen is I'm going to end up with 5. Okay, so that's my conjecture. Any number less than 10 that I sub in here, I'm going to end up with 5. Now we're going to do deduction. We're going to prove this is true. So choose a number less than 10. X, add 4, x plus 4. Double it. Make sure you multiply both of them by 2, 2x plus 8. Add on 7. 8 plus 7 is 15. Add on the original number. Well, our original number is x. So that would be 2x plus 1x is 3x, the kids tell me. Divide by 3. That's x plus 5. Divide them both by 3. Subtract the original number, which was x. X minus x is 0. So there it is. We just proved using deduction that our conjecture was any number less than 10 following this number game will end up with 5. And we just proved it. So there it is, friends. That's a common one that we see quite a bit of, the little number game case. So we proved it. Okay, let's do just a couple more, friends, and then you should be set. Okay, use deductive reasoning to prove the following statements. The sum of two even integers is always even. So remember, even integers we write as 2n or 2k. I see a lot of 2k's. So the sum means I'm going to add them together. That's 4n. And that's even because I can factor out a 2. Done. Okay, there it is. And if you want to tell me that your proof is done, you put this little black box. It's called the tombstone, which sounds kind of creepy. It means I'm done. Okay. Maybe you want to make a sentence saying, because I could factor out a 2, it's even. Okay. The sum of any 3 consecutive even numbers is divisible by 6. Okay. Let's think about this one for a second. I'm going to pick an even number, 2. The next consecutive means the next one, 4. The next one is 6. So how do I write this in deduction? Well, my first even number is, I'm just going to write 2k because I keep saying some people use 2k. That's my first one. My next consecutive even would be my first even number plus 2. And my third consecutive one would be my original one plus 4. There we go. Now, induction tells me I add those together and I certainly get 12. So that's divisible by 6. I can see that. So here I'm going to add these together. What I'm going to get is 6k plus 6. If it's divisible by 6, I better be able to factor out a 6. Look at right there. I did. Tombstone, I'm done. Okay. Ooh, a couple more. A few more. Okay. The sum of any 3 odd numbers is an odd number. Okay. So remember, an odd number we could call 2k plus 1. I got 3 of them. Doesn't tell me anything about them. So I'm just going to add 3 odd numbers together. What do I get? 6k plus 3. I know this is odd because I cannot factor out a 2, which means it's not even. So if it's not even, therefore it's not even, guess what? Therefore it has to be odd. Okay, so when you're trying to show me something's odd, you're going to show to me that it's not even first. All right, last 2, friends. We're almost there. This is a long one today. A product of any 2 odd numbers is odd. Okay, so product means we're going to multiply. 2k plus 1 times 2k plus 1. So when we multiply that out, we get 4 squared plus 4k plus 1. I want to show it's odd. So what I'm going to say is it's not even because I can't factor out a 2. So I know it's not even because I can't factor out that 2. Therefore, we have to be odd. Boom. Done. All right, last one, friends. The difference of squares. Okay, so we're going to square a couple things. Difference means subtract of 2 consecutive even numbers. Oh my goodness. Okay, so my first even number is 2n. So I'm going to square it. The difference means I'm going to subtract of 2 consecutive. So my next even, I would add 2 to the first one to get the next consecutive. Okay, square stuff. So 4n squared minus, okay, I got to be really careful here. This is 2n plus 2 times 2n plus 2, like that. Okay, so there's some algebra in deductive reasoning sometimes. Okay, I got that minus, there's that bracket. Okay, I'm going to distribute everything here. I'm going to get 4n squared plus 4n plus 4n plus 4. Okay, now I'm going to drop my brackets here. 4n squared minus 4n squared is 0. They cancel. Okay, I'm going to get 8n, but negative 8n minus 4. I want to prove that this is divisible by 4. So look at, I'm going to factor out a 4, and I get minus 2n minus 1. That, being able to factor out a 4 right there, makes this divisible by 4. Okay, friends, that was a lot. Deductive reasoning, pretty tricky stuff. You got to practice it. You got to know some definitions.